friends, welcome to my channel Maths Practice. Today we are going to discuss the first chapter of NCERT, which is real numbers. First we will discuss the key concepts and examples based on it, and then at the end we will discuss all the important practice examples which will cover the whole chapter. Now, real numbers consist of rational numbers and irrational numbers. A rational number is a number which can be expressed in the form of p by q, where q is not equal to 0 and p and q are integers. Now, before knowing what are rational numbers, first of all, let us see what are natural numbers. Natural numbers are numbers 1, 2, 3, 4 and so on. When you include 0 with the natural numbers, we get the set of whole numbers. So, whole numbers are 0, 1, 2, 3, 4 and so on. Integers include negative numbers in addition to whole numbers. So the set of integers is all the negative numbers 0 and all the positive numbers. And then rational numbers include all the integers. That means rational numbers include integers, whole numbers, natural numbers, and in addition to that all other numbers which can be expressed in the form of p by q or its decimal representation. For example, minus 4 by 3, 0.12, etc. Now the numbers which are not rational numbers, the real numbers which are not rational numbers are called irrational numbers. For example, root 2, root 5, root 7, pi, etc. First concept is Euclid's division lemma. Given positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r, where r is the remainder and it can take values between 0 and b. Let us take an example to understand. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Now suppose a is any positive integer. What does the division lemma state? The division lemma states that we can express a in the form of a is equal to bq plus r, take b is equal to 3. So r can take values between 0 and 3. So the remainders r can take the value 0, 1 or 2. It means a can either be 3q or 3q plus 1 or 3q plus 2. Now suppose if a is equal to 3q, squaring both the sides, we get 3q whole square is equal to 9q square, which is in the form of 3 into some m. If suppose a is 3q plus 1, again squaring we get 9q square plus 6q plus 1. Taking 3 common, we get 3 into 3q square plus 2q plus 1. So actually it is in the form of 3 into some m plus 1. Suppose if a is equal to 3q plus 2, squaring both the sides, we get 9q square plus 12q plus 4. 4 can be written as 3 plus 1. So again taking out 3 common, we get 3q square plus 4q plus 1 plus 1. That means it is in the form of 3m plus 1. So it can be either in the form of 3m or it can be in the form of 3m plus 1. Another example, use Euclid's algorithm to find the HCF of 441, 567 and 693. Since there are three numbers, first we will find the HCF for 441 and 567. According to Euclid's lemma, we will write 567 as 441 into 1 plus remainder 126. Again 441 can be written as 126 into 3 plus 63. 126 is 63 into 2 plus 0. Since we have got the remainder 0, HCF of 567 and 441 is equal to 63. Similarly, now we find HCF of 63 and 693. 693 is 63 into 11 plus 0. So the HCF is 63. Hence, the HCF of all the three numbers is equal to 63. There are two other practice examples which are given with the answer. You can try them. Next is Theorem 1.3. Let p be a prime number if p divides a square, then p divides a, where a is a positive integer. We can prove that root 2, root 3, root 5, root 7 all are irrational. Let us prove that root 5 is irrational. Let us assume to the contrary that root 5 is rational. Now by the definition of rational number, if root 5 is rational, we can write it as root 5 is equal to a upon b. Suppose a and b have a common factor other than 1, then we can divide by the common factor and at last we can obtain a and b such that they are co-prime. Root 5 is equal to a upon b, so b root 5 is equal to a. Squaring both the sides we get 5b square is equal to a square. Hence a square is divisible by 5. 5b square is equal to a square, so a square is divisible by 5. By above theorem, a will also be divisible by 5. Now since a is divisible by 5, we can write a is equal to 5 into c for some integer c. Substituting a is equal to 5c, we get 5b square is equal to 5c whole square, or 5b square is equal to 25c square. This shows that b square is equal to 5c square. So b square is also divisible by 5. Hence b is also divisible by 5. So we have got two things. A is divisible by 5 and b is also divisible by 5. Shown that a and b both are divisible by 5. Hence a and b have at least 5 as a common factor. But this contradicts the fact that a and b are co-prime. This contradiction is due to our incorrect assumption that root 5 is rational. Hence, we can conclude that root 5 is irrational. Similarly, we can also prove that root 7, root 3 are irrational. The next example says that prove that 3 plus 2 root 5 is irrational. We have already shown that root 5 is irrational. Now we want to prove that 3 plus 2 root 5 is irrational. Let us assume to the contrary that 3 plus 2 root 5 is rational. Again, we can find co-primes a and b such that 3 plus 2 root 5 is equal to a upon b. Now, just rearranging the equation, we get 2 root 5 is equal to a upon b minus 3. Hence, root 5 is equal to a upon 2b minus 3 upon 2. Since a and b are integers, a upon 2b minus 3 upon 2 is also rational. Means root 5 is rational, which contradicts the fact that root 5 is irrational. And this contradiction is due to our incorrect assumption that 3 plus 2 root 5 is rational. Hence, we have proved that 3 plus 2 root 5 is irrational. Next is the fundamental theorem of arithmetic. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. Now let us use this theorem in the next example. Find the HCF and LCM by prime factorization method for 8, 9 and 25. Now 8 is 2 into 2 into 2, 9 is 3 into 3 and 25 is 5 into 5. LCM means the highest powers of prime, that is 2 raised to 3 into 3 square into 5 square, which is 1800. And what is HCF? HCF is the common factor between them, which is 1 here. Let us take the next example. Check whether 6 raised to n can end with the digit 0 for any natural number n. Now suppose if 6 raised to n ends with 0, it should be divisible by 5. That means its prime factorization should contain the prime number 5. But 6 raised to n is nothing but 2 into 3 whole raised to n, which is 2 raised to n into 3 raised to n. 5 is not there in the factorization of 6 raised to n. Only the primes 2 and 3 are there, and by the above theorem, they are unique. So 5 does not occur in the prime factorization of 6 raised to n. Hence, 6 raised to n cannot end with the digit 0. Thank you for watching this video. In the next video, we will see the remaining key concepts and practice examples. Please do like, share and subscribe to my channel, Maths Practice.